I have you loud and clear.
Hello. Welcome. Science.
And that is to say,
physics,
medicine,
nature,
or
space,
time,
the brain,
life,
the universe.
Hello, this week we're in for a little light relief as we explore how light-based technologies are delivering a brighter future in medicine and beyond. And what this sound has to do with preventing diarrhoea.
Plus, in the news, a new gene therapy for spinal muscular atrophy, scientists make sonic holograms, and the most accurate reconstruction of a dinosaur yet. I'm Chris Smith.
I'm Kat Arney, and you're listening to The Naked Scientists.
The Naked Scientists podcast is powered by ukfast.co.uk.
First this week, a new genetic test to diagnose individuals at risk of coronary heart disease at a much earlier stage has been unveiled. An international team of scientists married up over 49,000 inherited genetic markers called SNPs, single nucleotide polymorphisms, with whether or not 15,000 individuals carrying those markers had developed heart disease or not. This has enabled them to identify a pattern of markers that can together spell out the likelihood of a person going on to have heart disease later in life. And this means that it might be possible to intervene and ward off a heart attack before it even happens. Nilesh Samani is one of the study authors.
Heart disease is the commonest cause of early death in this country and in many countries around the world. There are many reasons, important lifestyle factors, smoking, lack of physical activity, having certain conditions such as high blood pressure and diabetes, high cholesterol. But we also know there's a very important genetic component to this. Perhaps about 50% of the risk of getting heart disease is related to an inherited component.
And so is that what you're probing with this present piece of research, trying to get a handle on how those genes play a role in the development of the disease and finding out who's got them?
In the last few years, we spent a lot of time trying to identify genetic differences between people which affect the risk of getting coronary heart disease. We found quite a few of these now. But this particular research takes us beyond that point and asks the question, if we had this genetic information on individuals, how well does it predict them getting heart disease?
If we know we already have these risk factors, are we not already pretty good at identifying who the people are who are likely to suffer a heart attack?
No, because two reasons. The risk factors like high blood pressure and cholesterol only explains part of our risk of getting heart disease. And to a large extent, the genetic factors that we've identified are independent of those. Some of them work through these risk factors, but the majority of them don't. So they provide independent information. What we know is that coronary heart disease, the underlying process, starts in when people are in their 20s. And at that stage, the risk factors we currently use are not particularly discriminatory between individuals. Whereas your genetic risk factors, you're born with them. And so we can look at them at any stage in one's life and therefore put people into different categories of what their genetic risk is.
And how did you do that?
So we created, from the studies we've done where we've identified the genetic barriers, we created a genetic risk score. And then on the basis of that risk score, we looked to see whether those individuals who had the highest burden of genetic risk, in the top 20%, versus those who had the lowest burden, what their lifetime risk of getting coronary heart disease was in a number of populations that we had access to around the world. And what you see is that if you were unlucky as an individual to have the top 20% of the genetic risk, then over the lifetime your risk of getting coronary heart disease was at least 5-fold higher.
Armed with that information, how do you propose that we use it?
Obviously, more work needs to be done to show that this finding can be applied to different populations and under different situations. But if we confirm that, then I think one of the things that we can do is to perhaps identify those individuals who are at highest risk much earlier, at a time when the process is developing silently, and to try and prevent it progressing by giving them advice about lifestyle, perhaps giving them some treatments such as statins at that very early stage in the disease process rather than waiting for the condition to develop.
Although the study doesn't tell you whether that intervention will work, does it? Because what it does say is you can identify people who carry these high-risk genes, but it doesn't tell you if we intervene in those people whether we can affect the outcome.
You're absolutely right. We have some evidence that they probably do, because in some other studies, investigators have shown that if you carry a high genetic risk burden and you give statins to those individuals versus people who carry a low genetic risk burden, then the absolute benefit from the statins is much higher in those who are at higher genetic risk. So we know that if you can identify people, even some of the treatments we have now are likely to be of benefit. But you're absolutely right that we need to do more studies to both demonstrate that having this knowledge would be beneficial, and secondly, that it is something that the public will accept in terms of screening, and finally, that it is cost effective for health to be able to supply it.
Let's hope so. That was Professor Sir Nilesh Samani from the University of Leicester. He's also the medical director of the British Heart Foundation, which funded that study. It's just been published in the European Heart Journal.
Now, take a close look at your bank card or passport and you'll probably see a hologram used to make the document harder to fake. The surface of the hologram is minutely textured, embossed with tiny bumps that are the code for an image. When light waves bounce off the surface, they reconstruct the image so that it appears to float in midair. Now, researchers in Germany are applying the same principle with sound waves. They 3D print a piece of plastic to create a sonic lens that shapes sound waves emerging from an underwater speaker so that they form an acoustic landscape. This could be used to move cells around in a dish or even to treat diseases inside the human body. Laura Brooks heard how it works from inventor Andrew Mark.
So what we're trying to achieve is controlled shaping of the sound field. We'd like to have particular areas that are high intensity and other areas that are low intensity. And we do that through what we call an acoustic hologram. The idea is that we have a transducer, and the transducer is basically a speaker. It projects a sound wave through the hologram, and the hologram acts effectively like a lens to modify that sound wave so that in the far field or downstream of the hologram, we have a well-defined shaped sound field.
So can we think of it as something like a landscape that has hills and valleys of sound, effectively?
That's exactly right. So the hologram itself is a 3D piece of printed plastic, and it has topography to it. So certain pixels within the hologram are higher or taller than others, and because the speed of sound within the hologram is different than within the water in which it's immersed, the waves have different phase when they leave the holographic plate.
And what kinds of patterns are you making, and what would you use them for?
So one of the things that we tried to do is create a two-dimensional image downstream from the hologram. And we can shape that image into the shape of a dove, for instance. And we use that to do particle collection. So we have many, many small microscopic particles that collect in the sound field into the shape of the dove.
So you're drawing pictures then with these sound landscapes?
Exactly right.
That's really impressive. What else can you do with them?
So one of the other things that we can do is we can change the arrangement of the hologram and project sound upwards towards the surface of the water. So the hologram is underwater and it projects sound waves up to where the water meets the air. And where there's high sound intensity, we get crests forming in the surface of the water. And if you put particles onto the crests, then the particles are trapped there. And so one of the nice things that we can do is shape the profile of these crests so that they don't just have simple points, but they're instead linear tracks, for instance. And the other nice thing is because we have such complexity in this hologram, we can actually build a phase gradient into the track. And the phase gradient serves to actually push the particles. So now we have a track that the particles are confined to, and a phase gradient that pushes them along the track. And we can make these tracks into shapes like, for instance, letters, or we can do rings, and we can have multiple rings. And in some cases, we can have particles that move in opposite directions depending on the direction of the phase gradient along these rings.
So you can actually move things around without even touching them, just using these sound fields?
Exactly.
And so you've talked about assembling these tiny particles, but what could this be used for in terms of practical applications?
So one of the things that we have in mind is to use it for either therapeutic or diagnostic medical imaging. So one of the applications that ultrasound is used for right now is for either ablation or for thermotherapy, where it's used to heat things deep inside of the human body. We can imagine a scenario where a doctor takes an image of the patient's body, a particular patient, figures out what the best way or the best distribution of sound field inside of the patient's body is, crafts a hologram by 3D printing that is specific to that patient, and then uses that hologram to heat or ablate in a way that's particular to that patient's needs.
Fascinating and simple in equal measure, isn't it? That was Andrew Mark. He's at the Max Planck Institute for Intelligent Systems in Stuttgart, and that work was published this week in the journal Nature.
She made biologists think differently because we showed that cells can be changed. So I may be the father of Dolly, but I think I'm the grandfather of iPS cells.
Hello, Dolly. In this month's Naked Genetics, we're commemorating 20 years since the birth of Dolly the sheep, the first mammal cloned from an adult cell, and the transformative technologies that followed. Plus, our gene of the month is keeping a straight face. Listen and download now at nakedscientist.com/genetics.
You're listening to The Naked Scientist with me, Chris Smith, and with Kat Arney. Later in the programme, we've all used Wi-Fi, but what about getting your light bulb to go online? Before that, though, it's time for our regular misconception. And this week, Kat, you've been sifting through the sweetie jar, haven't you?
I certainly have. Now, picture the scene. A kid's birthday party, complete with a table laden with sugar-packed goodies. Just a few slices of cake or chocky bickies seem to turn the mildest child into a hyperactive monster, quickly creating a situation of knee-high near anarchy. But while it's a commonly held belief that dosing kids up on sugar makes them hyperactive and badly behaved, like a badly organised pile of party cookies, the scientific evidence behind these claims just doesn't stack up. Brave scientists have actually carried out research into the links between children's diet and their behaviour, dating back more than 20 years. For example, in 1994, scientists published a major study in the New England Journal of Medicine describing a 9-week-long placebo-controlled trial looking at the effects of sucrose, that's regular table sugar to you and me, and the artificial sweetener aspartame on the behaviour of nearly 50 preschool and school-age kids, including children whose parents reported them as being particularly sensitive to the sweet stuff. Although it's difficult to carry out these kinds of studies with 100% accuracy, kids will be kids after all, and it's hard to completely control what they eat and do, and they're usually only involving a relatively small number of participants. The researchers concluded that neither sucrose nor aspartame produces discernible cognitive or behavioural effects in normal preschool children or in school-age children believed to be sensitive to sugar. This finding was backed up by another paper published in 1995, which again concluded that sugar does not affect the behaviour or cognitive performance of children. However, a small effect of sugar or effects on subsets of children cannot be ruled out. So, given that the studies say that there's either no effect or maybe only a tiny one, why do parents still swear that sugar turns their little angels into little monsters? It actually seems to come down to parental expectations. Put simply, if parents see their children eating lots of sugary food, they believe that they're going to act up and so attribute any naughtiness to the sugar. This was even tested in a placebo-controlled trial with mothers and sons, where half the mums were told their children were necking a sugary drink, while the others were told they were getting a drink with artificial sweetener, even though they were all given the artificial sweetener rather than the sugar. But the mothers who thought their sons had drunk lots of sugar were more likely to say their child was acting up. And the mums themselves actually criticised these apparent sugar-drinking kids more and watched them more closely. In fact, sugary drinks seem to alter parents' behaviour rather than children's. If you believe sugar is going to make your child behave badly, that's what you're going to be looking out for. And it goes without saying that kids' parties are ground zero for reinforcing this idea. Lots of sugary foods on offer, plus overexcited kids doing lots of fun activities that get them hyped up, and an expectation from parents that this will be a living nightmare. But it's more likely to be that expectation, along with the general excitement of the event, that's responsible for unruly behaviour, whether real or imagined. There's still research going on to find out whether sugar, or indeed artificial sweeteners, have any link to childhood conditions such as ADHD, but for now there isn't enough hard evidence to be sure. Of course, no one's saying that it's fine to let kids guzzle on sugary drinks, cakes and chocolate bars all day long. There are plenty of good reasons for kids, and adults, to keep an eye on the amount of sugar in their diet. For example, eating lots and lots of sugary food increases the likelihood of obesity, which can cause problems later in life. But bad behaviour doesn't seem to be one of them.
So sweet of you to say. Thank you, Kat. And if you have a potential misconception at home that you'd like us to look into, send it in to chris@thenakedscientist.com and we'll take a look. Next, a gene therapy breakthrough for an inherited motor neuron condition called spinal muscular atrophy, or SMA, has been unveiled by scientists at Oxford University. Patients with SMA can't make sufficient amounts of a protein called SMN, short for survival motor neuron, which is coded for by a gene called SMN1. What Susan Hammond and her colleagues are announcing this week is a DNA sticking plaster, or patch, that can boost the activity of a backup gene called SMN2 that can make up for the missing SMN1. The way they get this genetic patch into the affected cells is by coupling it to a short protein or peptide. The technique restored a normal lifespan to mice with the animal equivalent of spinal muscular atrophy.
Spinal muscular atrophy is an inherited disorder that mainly affects children that starts to present between 0 and 6 months of age. It results in death in the motor neurons in the spinal cord, and these motor neurons, they reach out into the skeletal muscle. So when they die, the skeletal muscle becomes disused and it starts to become degenerated. It's caused by a mutation in the survival motor neuron gene, the gene that's inherited for creating SMA.
Given this is a genetic disorder, how might we be able to tackle it then?
So in SMA, we have two forms of the gene that causes SMA. We have SMN1 and SMN2. And in most of us, SMN1 is fully functional and will give all the protein that is needed to survive and to be healthy. But in patients, there's mutations or deletions in SMN1. So we are left with SMN2, which only gives about 10% of this protein that you need, which isn't enough for survival. So what we try to do is we try to enhance the amount of protein that SMN2 gives.
So there are two genes, SMN1 and SMN2. Mm-hmm. A healthy person who doesn't have this condition has a normally working copy of both, mm-hmm. but SMN1 produces the vast bulk of the protein that you need from that gene. And in people who have damage to that gene, they get this condition, but they do still have the SMN2 gene limping along. And you're saying, can we pep that up in some way in order to bring them up to the level that would make them healthy?
Yeah, so we're quite lucky to have the SMN2 gene that every patient has. So with one kind of treatment, we can target almost 100% of the patients.
Right, so how do you try to persuade SMN2 to rev up its production so that it produces enough of the stuff you need to keep the cells healthy?
So in SMN2, it creates a product which isn't what we would call functional. And what we've designed is these short bits of DNA, which act as a patch in which it can combine itself very well onto these products and therefore make it a functional product.
How do you get those patches into the cells that need them?
On their own, it's very hard to get these patches into the cell. We have designed something which we call peptides, which you could think of as like a passport or a key that you add to these patches. And that really allows these to get into the cell that is required.
How do they work? How do they do that?
It's a little bit unclear. It's very nonspecific. It's the type of charge that these peptides have. And it seems to allow uptake of these patches into the cell.
So you have a lump of protein, these peptides, which you couple to the patch. So one's holding hands with the other, and the passport, the peptide, gets it into the cell, and then the patch, the short sequence of DNA, does the business once it's in the cell.
Yes, exactly.
And does it go everywhere in the body, or does it target the delivery to those motor nerve cells that are most vulnerable in this condition?
It goes everywhere in the body.
So how do you know this works? What tests have you done to show that this has got legs?
We've treated mouse models of SMA that are very, very severe. So these models will only survive till about 12 days after birth. And when we introduce these peptide patches into these mice on the day that they're born, they increase their survival to around a mean of 456 days.
From what, a daily dose or once?
Twice. It's the day of birth and then 2 days after.
Good grief, so 2 doses is enough almost to give these mice a normal lifespan, because mice don't live that long, do they?
Yes, it's essentially a normal lifespan.
And it goes into the bloodstream?
Yes.
What about the function in these mice? I know you're saying that they have a normal lifespan, but do they appear to be functionally normal? Do they get muscle problems, or do they appear not to?
They're essentially normal. They're as strong as normal mice. They are bigger than untreated animals. And they're what we call neuromuscular junctions, which is the area where the nerve hits the muscle. That's completely normal as well.
And do you think that this protein, the peptide passport, will also work in humans?
Well, we certainly hope so. If you inject pups the day that they're born, we say that they have sort of less developed biological barriers, so it would be a bit easier for this to get through the body. But we can do it in the adult animals, and in the adult animals, we still see it getting into the brain and the spinal cord. And so we really hope that this will translate into humans.
And so the next step?
Well, the next step is to try to make this a clinical trial. We are working to get this through all the things that need to happen to put it into a clinical trial, the safety data and that sort of thing. And then in a couple of years, we hope to start recruiting for a clinical trial on this.
A story I'm sure we'll need to come back to. That was Susan Hammond, and the study came out this week in the journal PNAS.
That is absolutely fantastic, hopeful news. Scientists from the University of Bristol have revealed the most accurate reconstruction of a dinosaur ever made. A fantastically preserved fossil found in a lake deposit in China has revealed not only the colouring of the creature, but also where it lived before it found itself at the bottom of a lake. Georgia Mills spoke to researcher Jakob Winter from the University of Bristol to get to know this Cretaceous character.
Well, the dinosaur is called Psittacosaurus, which means the parrot lizard. The derivation of the name comes from the fact that it's got a beak that kind of looks like a parrot's beak. And so this is a distant relative of Triceratops, and it's about the size of a Labrador. And it's from some deposits in northeastern China in the province called Liaoning that we find these fossils in, which is about 120 million years old.
I looked at some of the photos of this, not photos, obviously, some of the reconstructions of this dinosaur from your paper. And it's quite cute. It's got these little sort of cheek horns that stick out at the sides and looks like quite a friendly vegetarian.
Yeah, this dinosaur was definitely extremely cute. Now that we finally have a reconstruction and an idea of like how this dinosaur looked like, we can see that it's exorbitantly cute. It kind of looks like somewhere between like maybe E.T. and then I don't know what else we can compare to. But it kind of like looks like E.T. It's got like sort of very sort of cute white face, but then it has these like very like white cheek horns that makes it look very, very distinct.
And what have you been investigating for this dinosaur?
We have been looking at a fossil of this Psittacosaurus, which is extremely well preserved. What we have is remains of the skin associated with the skeleton. And Psittacosaurus is a fairly common fossil in these deposits in northeastern China. But occasionally we get some of these specimens that got washed out into these lake deposits. And this one is really, really complete and really, really well preserved. And so we have looked at these skin impressions and we find organic residues in these. And we've recently discovered that when we have organic remains in, for example, feathers preserved in dinosaurs, we have the pigments retained in these. And we can look at these pigments, which is melanin, and make some inferences about the original colors and color patterns that this dinosaur would have had. So now we've done the same thing with this dinosaur. We have looked at these organic residues. And when we look at them under a so-called scanning electron microscope, then we find little structures which are melanosomes. And so that demonstrates that what we have preserved in this fossil is the melanin pigment that gave the color to the animal.
Okay, so you've actually found sort of the fossilised remains of pigments, and that has then in turn informed you of what this dinosaur's colouring looked like. So what can this tell you about the dinosaur other than helping you have these lovely reconstructed paintings of it?
Well, so that's the interesting thing. We can also say something about what this dinosaur was doing because it had these color patterns for a reason. And these color patterns that we see in this dinosaur are various types of camouflage patterns. And the most important one, which is the one that we best can use to say something about the environment that it lived in, is this transition in light to dark between the back and the belly and the tail of the animal, which is this pattern called counter shading.
So putting everything together, and we've got a Labrador-sized dinosaur. It's got a body kind of like a chubby T-Rex, and the head looks confusingly like a cross between E.T.'s and a parrot. Also, there's some weird grass-looking stuff sticking out of its tail. and then the colouring is the speckled black and red on a tan body, which is much darker on the top. And this is what Jakob referred to as countershading. Countershading is a clever technique that's still used by animals today. It involves having a lighter underside and a darker back. Think about things like penguins, deer, rabbits, they all have lighter bellies. And this basically makes you look a lot less conspicuous. Our brains are trained to spot objects when they're lighter on the top and darker on the bottom, as that's how the sun tends to light things up. But if you counteract this with your shading, countershading, you tend to appear more flat, and this makes it easier to avoid being eaten as predators have a harder time spotting you. So this dinosaur seems to have been using this trick over 100 million years ago, and this also tells us something about its environment.
Because what we see in living animals is that the countershading varies depending on the habitat that they live in. And the reason why is because the light conditions will vary depending on where you live. So the countershading in animals that live in savannas, for example, are usually sitting very high on the body and they're very sharp, whereas animals that live in forest, they have a countershading which is much more gradual and it sits much further down on the body. So basically, it means that we can use this sort of evidence to go back to reconstruct this dinosaur and put the original color patterns onto it. And we can show that it lived in a habitat which was a forest.
So E.T.'s known home, or I suppose since it's a fossil, E.T.'s bone home, you could say. First time I've ever heard a dinosaur likened to E.T. That was Jakob Winter, and he published that study in Current Biology this week.
This is The Naked Scientists. I'm Kat Arney. He's Chris Smith. If you'd like to get in touch with us, you can email chris@nakedscientist.com, find us on Facebook or tweet @nakedscientists.
Now it's time for a little light relief as we talk to a host of luminaries, do you see what I did there, about how they're using light to change the world. First up, contaminated drinking water is a major source of disease in poor countries. Thousands of children die every day from waterborne illness. Fortunately, Cambridge scientist Richard Bowman is working on a low-cost solution called WaterScope. Now that's the sound of a 3D printer, which Richard is using to make handheld plastic microscopes that can test the water samples he's looking at for infectious diseases. Richard's with us now. Richard, how did this project get started?
Well, it got started about a year ago now when a student project looking into how we can do water testing faster and more cheaply came up with the idea of using a microscope to essentially shrink existing tests and do them much faster. What the microscope does is tell us whether particular water is clean or dirty. Normally you do this by collecting some water and incubating it overnight with some nutrients for the bacteria. Then the following day you can see the colonies of bacteria with the naked eye, and that's how you tell whether the water is clean or dirty. If we do the same experiment under a microscope, you can see the bacteria after more like an hour, and so you can get an answer much more quickly.
Now that's very laudable, but of course people in poor countries can't afford expensive high-end microscopes, which is presumably why you're going down the route you are.
Absolutely. We want to make the microscopes very cheap, very easy to use, and ideally we want to be able to make them in the countries where they're needed, to avoid having to sort of ship stuff in from the UK, which is very expensive.
But if you are making the case that a poor person can't afford an expensive microscope, can they afford an expensive 3D printer?
Well, we don't need every person that has to test their water to have a 3D printer, but we're starting to see labs setting up where they do have 3D printers, and they're looking for ways that they can use these to produce useful products, like, for example, our microscope.
So how do you 3D print a microscope, and are they any good?
They actually work really surprisingly well. The trick that we've used to make the microscope is quite an old one. Essentially, we take the wide-angle lens that you find on most webcams and turn it upside down, put it slightly further away from the camera sensor, and it becomes really quite a good little microscope objective. The other ingredient is holding your sample in the right place and being able to focus it. And we do that by essentially, instead of sliding stuff around, which is hard to do on roughly made 3D printed components, we use the flex in the plastic to actually bend the structure to move the sample into focus and move around on it.
That's very clever. So how do you actually build one of these things? Just talk me through piece by piece. Is it like Airfix? You know, those kits where you used to make a little aeroplane from pressing out the things, some of them the size of about a proton, from what I can tell, and assemble them into a working gadget?
Yes, it is a bit like that. The microscope prints in, I think it's 10 or 11 pieces, depending on exactly what you build. Most of it actually prints in a single piece, so all of the sensitive flexure mechanism that handles focusing it and translating the sample comes off in a oneer. Then you have to add in 3 screws, which is what you use to move the stage around and to focus the microscope, and snap in the camera and the optics. So the whole thing, well, it takes me about 20 minutes, half an hour, but I've built quite a lot of them now.
But even so, that's not long, is it? And the proof is in the pudding, though. Does it work? If you take a sample of dirty water from a puddle or a river and put it under the microscope, can you see whether or not there are germ-forming bacteria there?
Absolutely, we can. We're still working on some of the sample collection stuff, so going from the dirty water to something on a microscope slide that we can image. But the imaging part works really well, and the rest of it we hope to have sorted out in the next couple of months.
And once it is sorted out, how does it get deployed and where are you targeting?
In the first instance, we'll do a few small trials with a couple of partners, take it out to places where they're already doing water quality monitoring and sort of test our system versus theirs. Once we've established that it's all working nicely, we would work with the same partners to start getting testing kits out with their aid workers so that they're being used by someone that will feed back to us how they're working and how we can make them better.
And can you also effectively establish a surveillance network by having lots of these on the ground in lots of countries afflicted by waterborne illness problems? Does this give you data that you can then share in order to anticipate need for healthcare and also tell people there's a problem coming, don't drink the water?
Yeah, exactly. I mean, one of the most powerful things about it is that it's all built around a computer, in this case a Raspberry Pi. So all of the test results are digital, and we can send them back and build a database and sort of map out where the problem is.
Richard, thank you very much, and we wish you luck with the project. You'll have to come back and tell us about it and tell us how you're getting on. That's Richard Bowman from the University of Cambridge with the WaterScope project. Kat, over to you.
While WaterScope could help prevent disease, imaging using visible light also plays an important role in understanding and treating diseases already present in the body. Now, joining us is Sarah Bondyke, whose vision lab at the University of Cambridge is using light to fight cancer. Hi, Sarah. So tell us a bit about this. How important is imaging, being able to see stuff, to fighting cancer, to diagnosing it and to treating it?
Well, imaging is very important in the journey of a cancer patient. So if you think about the development of the disease early on, many of the symptoms of cancer are non-specific. So patients will often go into their GP and report these non-specific symptoms, who will refer them into the hospital. Now, if we didn't have imaging techniques like X-rays or magnetic resonance imaging, MRI, then we'd have to surgically open up the patient and search for the tumour mass.
Oh my God.
So having these non-invasive imaging techniques allows us to non-invasively have a look inside the patient and search for any abnormal lumps and bumps which shouldn't be there in the normal anatomy. So it's very important at diagnosis, but then it's also very important when we come to treatment, for example. So if we think about setting up radiotherapy, many solid tumours are treated with doses of radiation which are shaped and formed to target the tumour mass. And if we weren't able to see non-invasively where that mass was, then we might misdirect our dose and could cause side effects to off-target tissues. So it's important in diagnosis and treatment, and then many patients undergo follow-up, so they'll come back routinely to the hospital to have scans over time to check that their tumour is shrinking, and so that's how we manage to monitor that the tumour is responding to any therapy that's been given.
So you've mentioned a couple of techniques, CT, which uses X-ray, MRI, which uses kind of magnetism, but what are you doing? You're using a different form of waves, aren't you?
That's right. So we're trying to use visible light and light that's just outside of that visible region. And the reason for that is that CT and MRI and other conventional imaging technologies that we're familiar with in hospitals are relatively expensive and require patients actually to go into the hospital and have a scan that's operated by a specialist person. If we could make kind of more cost-effective technologies that could be distributed to GP surgeries, for example, then we might be able to actually improve the journey of the cancer patient, where they can get a more a faster diagnosis rather than having to go into the hospital.
You've got a little demo here to demonstrate one of the techniques that you're using. Talk me through it. What's the technique? And show us how this actually works.
So the technique is called photoacoustic imaging, and it's based on a physical concept called the photoacoustic effect. And this effect is quite readily understandable. If you think about going out into the sunshine on a hot day, the light energy that the sun is beaming down will be converted into heat energy in our skin. So light is often converted into heat. So that's the photo part of the photoacoustic effect. So the acoustic part is the heat being converted into sound. So the advantage of this technique is that we can measure how light is absorbed in tissue, but we can image it using sound, which penetrates much more deeply into the tissue. I mean, we know that we can't see through each other, so that means that visible light doesn't penetrate very deep into the tissue, but sound does. And so using the combination of light energy to create sound means that we can get much better images.
So you've got a nice little demo here. How does this work?
So the demo that I've got is a Coke Zero can. So if anyone's...
Other sugary drinks are available, non-sugary drinks.
Thanks, Kat. The reason for using this is that the can is a black coating on it. So black is a very strongly absorbing of light. You can do this at home with any regular camera flash that you have in your house. So I'm going to now put the camera flash right up close to the Coke can.
So about how far away would you say that is?
So about a centimetre from the Coke can.
Away. Okay, flash right up.
And I'm going to flash it. And you hear a little ping of the Coke can.
That's like someone's kind of flicked it with a finger.
Exactly. So I'll just do it again so everyone can hear it well.
Wow. Okay, so that is the light basically being turned into sound.
Yeah, so that's the energy coming from that camera flash being turned into a ping of sound. And so that's what exactly we're doing with the photoacoustic effect when we use it for imaging cancer. So we send a ping of light in this case we use a pulse of laser light, and that pulse of laser light gets absorbed and it produces a sound wave, which we can detect using regular ultrasound transducers, the same systems that you would use when you were imaging, say, a fetus during pregnancy. And we can use those to detect the sound.
So you're listening to the light coming back at you.
Exactly. And so the advantage of doing this is that ultrasound penetrates much deeper into the tissue than light does, but light gives us much better contrast. So when we do ultrasound imaging, we're just looking at reflection of sound off of boundaries. So we're not looking at any kind of specific molecular information or any functional information. Whereas when we use light is absorbed by a number of different molecules in the body, including hemoglobin in our blood cells. And hemoglobin has a different absorption spectrum, so it absorbs light differently and with different colours, depending on whether it's bound to oxygen or not. So that means in a tumour, we would be able to develop a map of the level of blood that's present in the tumour, so how many blood vessels are feeding it, and also how well oxygenated that blood is, so how well the nutrients are being delivered.
So that kind of tells you how well it's growing, I guess. Thank you very much. That's absolutely fascinating. That's Sarah Bondyke from Cambridge University.
Now, light can also give us important information about a person's medical conditions in emergency situations, like their heart rate or how much oxygen is in their blood. And Laura Brooks has been to see how a new light-based device could help to save lives in this setting.
Morning.
Hello.
James.
Nice to meet you.
Nice to meet you.
I'm going through this way.
Come with me. This is James Baker. I'm a partner at Cambridge Design Partnership and I look after electronics and connected products.
This week, Cambridge Design Partnership, CDP, received 2 awards for developing a wearable medical device that could help medics save lives on the battlefield.
At the point of injury, the battlefield medic faces a very challenging situation. They're trying to rescue somebody, they're trying to keep them alive, and there's many distractions, there's probably significant danger. And the process that they go through is to look at breathing and heart rate and base the kind of care that they give off those readings. But measuring those parameters is quite challenging, and whilst they're measuring them, they're not providing care.
A challenging situation indeed, but CDP's first response monitor could support medics in their difficult task. The gadget uses light-based sensors, among other techniques, to measure a casualty's vital signs.
A little piece of focused technology that can give them those important parameters and let them concentrate on providing care brings real benefit and helps them to improve the casualty outcome.
The little monitor is only about the size of the top joint of my thumb. It has a small display screen on the front and a clip on the back, a bit like a clip-on earring, except that instead of clipping onto your earlobe, it clips on to your nose.
It needs to clip onto the nose because we're interested in measuring both heart rate and breathing rate. The heart rate can be measured using an optical technique, but the breathing rate we do by looking at changes in temperature and humidity that are influenced as you breathe in and out.
Can you talk me through how it works?
Yes, we shine light into the tissue of the nose, and that gets bounced around and diffused and reflected inside the tissue, and some of that gets reflected back to the device. And by looking at the amount of light that comes back, it's influenced by the amount of blood that's in the tissue of the nose. So that gives you a signal that relates to the heart rate, with blood being pumped into the nose and then moving out again.
Is that similar to how fitness trackers work that people might have at home?
It's exactly the same technique. So on many fitness trackers, you'll see a light on the back that's contacting the skin, and it's using exactly the same technique to measure the heart rate.
That's really neat. I've always wondered how they work. So what else can you sense with this device?
Staying with the optical technique, if we actually use two slightly different colours of light shone into the tissue of the nose, we can look at the fact that blood cells change colour dependent on how much oxygen they're carrying. So looking at the ratios of those two light wavelengths that come back to us, we can actually determine the oxygenation state of the blood.
So you record all of this data from the patient. What do you then do with that data?
So there's multiple levels of how we use and display that information. The primary method of display is that those three parameters are shown on the device itself. There's a nice little bright OLED display on the device. On the next level, we can actually communicate that information off to a wireless device, such as a mobile phone or a tablet. And that allows us to do two things. We can show for a single casualty how those parameters have changed or trended over time, but it also allows us to monitor multiple casualties, so you can start thinking about which one of my patients needs my attention most urgently.
You've got your smartphone here. Can you show me how it works?
Certainly. So you can see on this front page, we're currently connected to one device, and we're showing those three parameters of respiration rate, heart rate and SpO2 for that one device. We could have multiple devices connected to this front page. Or alternatively, you can dive more deeply into the information from any one device. So I'm pressing that one, and it's brought up some graphs that are looking at those instantaneous parameters, but it's also showing me graphs of how those parameters have changed over time. So you can see, for example, the breathing graph had me breathing at about 22 breaths per minute. But now you can see where I've taken the device off, and it's now trended down to 0 breaths per minute. I think if the device was still attached, that would be a big alert for you to actually go and have a look more closely at me.
Yes, certainly. James told me that this kind of monitoring also answers another key challenge in treating casualties in dangerous situations: how to keep information about the patient with the patient while they are transported to safety for further treatment. Since the wearable monitor stays with the casualty, the data that it records is automatically passed on to rescuers and is available to whoever is caring for them next. What's more, James thinks the monitor could give life-saving assistance in a range of different scenarios.
We originally started by investigating military uses, but we see lots of opportunities for this in all sorts of civilian first response situations as well, such as disaster relief or anywhere there's a multiple casualty situation. It can bring real benefit where you have first responders, people on the scene who have some level of medical skill, but they're not the professional emergency services, and they're trying to deliver care whilst they're waiting for the emergency services to arrive. This is a device that can give them a real insight into the immediate health of the patients. So you can see on the example here, we've got 3 casualties being monitored, and it's drawing our attention to casualty 1. It's showing that their blood oxygenation is dropping below a bound that we've set as considered to be acceptable, saying this person needs immediate attention from you.
What's next then for this device? Will we be seeing medics on the front line using these anytime soon?
So we've been through a process of checking this concept with various battlefield medics, and we're getting great feedback that this could be really useful to them on the battlefield. So we know there's a market for it, and we have a device that shows our concept works. And the next stage for us is looking for investment, building on the work that we've done to date and getting towards a product that we could sell in volume into that market.
And we wish them luck. That was James Baker from Cambridge Design Partnership, who was speaking with Laura Brooks.
Hello, Greya here from Naked Astronomy. I wanted to say hey and tell you about my new podcast. It's an awesome audio adventure into the big black cosmos that we inhabit. What's out there? How did it all begin? And what will happen in the end? Presented and produced by yours truly. You can find it on most podcasting platforms. Just search Naked Astronomy.
You're listening to The Naked Scientists with me, Kat Arney, and with Chris Smith. Now, wearable sensors like the first response monitor we just heard about wirelessly communicate patient information. But with more and more connected technology, we could be heading for a big problem.
And that problem is bandwidth. We're in danger of running out of radio frequencies to transmit all of our data. So earlier this week, I spoke to Harold Haas at the University of Edinburgh, and he's proposing a new solution. It's called Li-Fi, and you've guessed it, it uses visible light.
The traffic through our communication networks has increased rapidly, so that it will take a normal human being 5 million years to watch all the video traffic that is sent through the networks in 1 month. We have an exponential growth in data that we transmit through our networks. And many businesses are centered around data and access to data. And this is sort of the lifeline of the future economy.
Yes, indeed, because in an article you've written, and I quote, you've said, by 2020, the data deluge is predicted to increase to 44 zettabytes. I'd never even heard of a zettabyte. You say nearly as many bits as there are stars in the universe. So basically, we've got a data traffic problem. Everything is producing data, and we haven't got pipelines big enough to put it all down.
Yes, that is absolutely correct. That's why we at the University of Edinburgh are looking at different ways of transmitting data, i.e. looking at different pipes than we know at the moment. The classic pipe at the moment is the radio frequency spectrum, but the radio spectrum is part of a larger family, and the family is the electromagnetic spectrum. And a big fraction of the electromagnetic spectrum is also the visible light spectrum, which we have been exploring as a resource for data transmission.
So you're saying that rather than send things via Wi-Fi radio, we could use the light we can see?
Yes, that is absolutely true. We use the visible light, the lights that are around us, the lights in our ceilings, the street lights. And these particular lights are becoming more and more LED-based lights. And LEDs are electronic devices, and therefore they can be used to provide illumination. But this feature as an electronic device also allows us to change the intensity much, much faster than we can even think or see. And these very high speeds at which we change the intensity allows us to transmit and encode data onto the illumination or the light that illuminates us.
So effectively, the light in the ceiling could be made to get a tiny bit brighter or a tiny bit dimmer very, very quickly. And that would carry a code which would transmit information to, say, my laptop.
That's absolutely correct. And the laptop could have integrated another light source, which is outside the visible range in the infrared spectrum, and transmitting data back to the ceiling using the infrared. Then we have a bi-directional link.
And if we use ceiling lights in this way, how much data can we get through them? How fast can they transmit information?
That significantly depends on what kind of light sources we use. The fastest speeds that we can get at a moment is 10 gigabit per second from a single color. So if you have red, green, blue creating white light, you could think of 30 gigabit per second.
And the way you would see this being deployed is that, say, a company, an office, public space would have these light sources. They would be themselves connected to the internet, and they would be looking at what light is coming out of people's computers in the room, which would be people sending data to that hub, if you like, and it would then make the request onto the internet, the data would come back off the internet, and then the device in the ceiling would make the light flicker in just the right way to send the data down to your computer.
Yes, this is correct. Modern lights in the ceiling would not be connected with mains power. They would be connected with a data cable. It's called power over Ethernet. So the data connection provides the energy to illuminate. So you have a data connection to the light, and the data connection to the light is connected to the internet. So you have basically the internet brought to the light, and the light itself is then converted into flickering light, and that is then captured by the smartphone, and you get your data from the website request.
Now, what about if you've got that really rubbish desk in the office that no one wants? The one that's in full glare of the sun, or the one in the corner that's all shady and dark. Will it still work?
It's very important to recognize that sunlight will only very, very marginally affect the data rate. So that's the first point. And the second point is the light flicker is very, very small compared to the entire light output, which then also means that we can dim the light down to very low levels while we still maintain the capability of transmitting data at very high speeds.
That was going to be my question in terms of it doesn't sound good for the environment if we have to run the lights all the time during the day, but if we can turn the intensity of those lights right down so it doesn't waste a lot of energy, but we still get back the ability to transmit the data, then it's a good idea.
Yeah, that's absolutely the case. We can really reduce the intensity, and that's why we can also use it in street lights outdoors.
Now, this sounds tremendous, but have you got any evidence that outside of your laboratory this will work?
Yes, there's been a press release, in fact, this week. We are equipping a large office of a security firm in Paris. They don't use Wi-Fi because Wi-Fi penetrates through walls, whereas light will not go through a wall, and therefore it's much more secure to use light for data communication.
So it took about 10 to 15 years for Wi-Fi to become ubiquitous. Are we looking at the same sort of trajectory for Li-Fi?
Yeah, I think it will be faster, in my view. So it took 100 years for the landline telephone to have ubiquitous sort of coverage. It took 15 years for Wi-Fi, and I predict it takes about 5 to 8 years for full uptake of Li-Fi.
And Harold will hold you to that. That was Harold Haas from Edinburgh University. Thank you also to Sarah Bondyke, Richard Bowman and James Baker, who you all heard earlier. Now, to finish this week, it's time for our question of the week, and Connie Orbach has got all shaken up with this question from Gareth.
The Naked Scientist's Question of the Week, brought to you in association with the Houter Wisman Foundation, supporting science and education from Alpha to Omega.
Is it plausible to draw any kind of link between nuclear tests by countries like North Korea and the prevalence of earthquakes?
An intriguing question, Gareth. And it turns out you're not the only one thinking it, as Banesh also got in touch to ask, what is the relevance between nuclear power testing and earthquakes? Well, I didn't want to let everyone down now, so I asked Cambridge University's Alex Copley to help. So what's happening to the ground when there's an earthquake or a bomb blast?
In earthquakes, two big bits of rock are sliding past each other along a surface that we call an active fault. In an explosion, what's happening is the explosion is pushing against all the rocks around it. So both of these set up vibrations that travel through the earth. But because they involve different kinds of motion, in one case this sliding of rocks past each other, in the other case this pushing of rocks outwards, the vibrations that they set up are different. They have different characteristics.
Not completely the same. But still, could one cause the other?
That's a similar question to the sort of well-known question of can fracking generate earthquakes? Because you're doing a similar thing in both cases. You're sort of changing the forces in the earth. Both of them can generate little earthquakes on their own. In terms of whether they can generate a big earthquake, the kind of size of earthquake which is going to sort of damage buildings and things, that depends on whether there is already a pre-stressed and sort of ready-to-go fault plane nearby. So if you set off a bomb next to a big fault which is already primed and ready to go, then the little bit of energy you're putting in can tip it over the edge and you can generate a very big earthquake. However, the energy you're putting in is not enough to generate a big earthquake on its own. Unfortunately, we don't know much about where the big faults are and what the stress state on them is, so how close and primed and ready to go they are. So this means it's difficult to know before it happens whether bombs or fracking are actually going to generate a big earthquake or not.
This isn't making me feel particularly secure. What about South Korea? Is there any chance that their recent earthquakes could be linked to bomb testing in North Korea?
That's almost certainly a coincidence. There are earthquakes going off all over the place all the time. So if you say that you're going to look at everything within a hundreds of kilometre radius, then it's not a surprise that there's an earthquake going on there. It's just a coincidence.
Well, there you have it. Nuclear bomb testing could lead to an earthquake, but it's likely to be very, very small. Next week, we'll be getting our hands dirty with Dale's question.
Today at work, the safety lady tells me that regular hand soap doesn't kill germs. In fact, that's the reason why after y'all wash your hands for surgery, you do this, so the little boogers will just run off your elbows instead of down onto your fingers. Are you kidding me?
So just to explain, that was a video that Dale originally sent in, saying that after you wash your hands for surgery, you do this, and that's that iconic action in any hospital drama, where after washing their hands, surgeons hold them up in front of their faces. I'm sure you've seen pictures of it. So do you have an answer? Is it really worth doing it? Send it in to chris@nakedscientist.com, tweet @nakedscientists, or let us know your thoughts on our forum, nakedscientist.com/forum.
And that's it for this week. Thank you to Laura Brooks and Connie Orbach for production. Do join us again next time when we're going to be answering the questions that you have been sending in. Speaking of which, you can email chris@thenakedscientist.com if you've got something on your mind. The Naked Scientist comes to you from Cambridge University. It's supported by the STFC, the EPSRC and Rolls-Royce. I'm Chris Smith, and until next time, goodbye.